Welcome back to 4.4 Continued Differentiability. So a function of multiple variables like x and y is differentiable as long as it's smooth, just like functions in Calc 1. But how do we determine smoothness? In the case where we saw the tangent plane did not exist on that last surface, the surface looked continuous, but it definitely was not smooth. So there was a corner as long as we traveled along the path y equals x. If we were just looking at the equations of a function, however, we can determine differentiability without being able to pick that one specific path to find the corner on. So what we'll do is create this function. Sorry if you can hear that dog barking. It's my neighbor's dog, not mine. Can't do anything about it. Anyways, our function that we're starting with, f of xy, is differentiable if we can write this equation where the first term is essentially the tangent plane. So the first three terms here make up the tangent plane. Plus one other term, which is the error term. Remember that when we did linear approximations, we said that the tangent plane was an approximation for the actual function and that the function value would be slightly different from what the function L would give us. This error term is what calculates the difference between the approximation and the actual function value. If our surface is differentiable, then it won't have any sharp corners. It'll be nice and smooth, which means that when we find this error term, we should be able to plug it into this limit where we do the error term divided by the radius of the delta disk. And when we apply the limit, it should shrink down to 0. So if we want to demonstrate that a function is differentiable, the first thing we're going to do is create that representation of our function using our tangent plane plus an error term or error function. We know that to find the tangent plane, we need our function evaluated at a known point. In this case, we're using the point 2, 3. We also need our x partial as well as our x partial evaluated at the point. We need our y partial as well as our y partial evaluated at the point. Go ahead and calculate each of these 5 values. Plug them into the tangent plane portion of our equation, and then let's check our answers after you've had that. So once we evaluate our function and each of the partials, we can replace those in the tangent plane portion of our expression. We can also replace the definition f since we are given that in the setup of the problem. So we'll write 2x squared minus 4y on the left, and that'll be equal to 20 plus our x partial 8 times our change in x plus our y partial negative 4 times our change in y plus that error function. And now if we look at our expression, we can see that the only part that we don't know is this e of xy term. So what we should do is isolate it, move everything over to the left-hand side and simplify, or simplify first, however you want to do it. I'm going to go ahead and distribute my products first so that I can see if anything balances out on the left and right-hand side of my equation so that I can just cross them off rather than move them around. And I do notice that I have a negative 4y on both sides of the equation, so I'm going to cross those out, because if I added 4y to both sides of the equation, they zero each other out. I also notice that I have 20, negative 16, and negative 12. Those will add up to be negative 8. So we can clean up a little bit and rewrite our equation as 2x squared equals 8x minus 8 plus e of xy. And we need e of xy so that we can plug it into that limit, so we're going to isolate it. I'll add 8 to both sides. I'll also subtract 8x. Don't subtract the negative, that would be like adding. So that we find our error function, e of xy, looks like 2x squared minus 8x plus 8. And what we need to do is plug that into the limit where xy is approaching 2, negative 3, where we have the error function 2x squared minus 8x plus 8 in the numerator, and we have the radius of our disk in the denominator. That's the x minus 2 squared plus y minus negative 3 squared, all square rooted. And now we just need to evaluate that limit. So we need to evaluate this limit, but if we plug in using direct substitution, x equals 2, y equals negative 3, we'll get an indeterminate form. So the first thing we want to do is see if we can factor this. So let's zoom in on the numerator and do a bit of scratch work. I see that in my numerator there is a GCF of 2, so we'll factor that out. And then I also notice that what I have remaining when I factor the 2 out is a perfect square binomial, x minus 2 squared. So we're going to rewrite the numerator using this new factored form. And we're still at an indeterminate form. So we're going to have to get a little bit clever here. What I'd like to do is essentially rewrite the limit that I have here, but with one extra term in the numerator. So I want to add in one of these. But that wouldn't make this equal anymore. That would make it greater than or equal to. But that's going to allow us to simplify things. So let's go ahead and make that our next step. We're going to say the next limit is greater than or equal to that same limit notation. This time our numerator will look like 2 times x minus 2 squared plus y plus 3 squared. And if you'll notice, the reason why we're adding that in is so that we have similar terms in the numerator and denominator. Now, if we had something a little simpler, like if we had 2s divided by the square root of s, we know that with matching bases we can combine exponents. So we have 2 to the first s to the first power divided by s to the 1/2. We could just write that as 2 times s to the 1 minus 1/2, or 2s to the 1/2, or 2 root s. Now that's essentially what we're going to do here, where what I'm referring to as s is the sum of these binomials squared. So in the numerator, I have it like it's to the first power. In the denominator, I have those terms to the power of 1/2 because of the square root. So if I rewrite my square root as a power of 1/2, it looks a lot like what we have over here in our simplified version, which means we can rewrite the expression instead of 2 times these green parentheses divided by the green parentheses to the 1/2, we can write it as 2 times the green parentheses to the positive 1/2. Or if you'd like, you could write that as a square root. And now the denominator is gone because we combined those common bases. And technically, we should carry on our limit notation. And now we can do direct substitution without worry of any indeterminate form because there is no denominator. And when we plug everything in, we do find that this simplifies down to be 0. So we took our limit, we rewrote it, factoring the numerator. We used a clever addition of an extra term, and we said it's not equal to, but at the very least it's equal to. Otherwise, the calculation is going to be larger than. But we found that it was 0. So we're good to go. We showed that our function is differentiable because that limit expression was equal to 0.